Relations and functions. Hello students, today we will learn about relations and functions. Can anyone tell me what a relation is?
Two persons are said to be related if they have a connection between them.
Well said, Rita. The same concept works in mathematics, according to which two objects or quantities are said to be related if there is a recognizable connection or link between the two objects or quantities. For example, a relation AB belongs to A cross B represents that A is the brother of B. At the end of this lesson, we will be able to understand relation and its types, equivalent relations, functions and its types, composition of functions and invertible functions, binary operations, type of relations. Empty relation. A relation R in a set B is called empty relation if no element of B is related to any element of B. That is, R is given as null set being a subset of Cartesian product of B and B. Universal relation. A relation R in a set B is called universal relation if each element of B is related to every element of B, that is, R is equal to the Cartesian product of B and B. A relation R in a set B is called as reflexive if AA belongs to R for every A belonging to A, that is, every element is related to itself. Example, a relation is equal to on the set of a real number. Symmetric. If AB belonging to R implies that BA belonging to R for all A, B belonging to A, that is, if A is related to B, then B is also related to A. Transitive. If AB belonging to R and BC belonging to R implies that AC belonging to R or all ABC belonging to A, that is, if an element A is related to B and B is related to C, then A is also related to equivalence relation. A relation R in a set B is said to be an equivalence relation if R is reflexive, symmetric and transitive. Example 1. Show that the relation R in the set B of integers given by R equal to xy, where 2 divides x minus y, is an equivalence relation. Solution. Step 1. To check for reflexivity. The relation R is reflexive as 2 divides x minus x for all x belonging to z, that is, true for all x belonging to real numbers. Step 2. To check for symmetricity. If xy belongs to R, then 2 divides x minus y. Therefore, 2 divides y minus x. Hence, yx belonging to R, which shows that R is symmetric. Consider x equal to 4, y equal to 8, such that 4, 8 belonging to R. So x minus y is equal to 4 minus 8 equal to minus 4 is divisible by 2. Also, y minus x is equal to 8 minus 4 equal to 4 is divisible by 2. So 8, 4 belonging to R, which shows that R is symmetric. Step 3. To check for transitivity. If xy belongs to R and yz belongs to R, then x minus y and y minus z are divisible by 2. Now x minus z equal to x minus y plus y minus z is even, because sum of even numbers is even. So x minus z is divisible by 2. Consider 3 numbers x equal to 8, y equal to 6 and z equal to 4. X minus y equal to 8 minus 6 equal to 2 is divisible by 2. Y minus z equal to 6 minus 4 equal to 2 is divisible by 2. Now x minus z equal to x minus y plus y minus z. Finally, 4 is equal to 4. So 8 minus 4 is divisible by 2. Thus, R is transitive. Hence, R is an equivalence relation in B. Example 2. Let A be the set of all triangles in a plane with R a relation in A given by R equal to A1, A2, where A1 is congruent to A2. Show that R is an equivalence relation. Step 1. To check for reflexivity. The relation R is reflexive since every triangle is congruent to itself. Step 2. To check for symmetricity. We are given A1, A2 belonging to R, which implies A1 is congruent to R, 2 implying A2 is congruent to A1. This implies A2, A1 belongs to R. Hence, R is symmetric. Step 3. To check for transitivity. We have A1, A2, A2, A3 belongs to R, which implies A1 is congruent to A2 and A2 is congruent to A3. Thus, A1 is congruent to A3. This implies A1, A3 belongs to R. Thus, R is an equivalence relation. A function is defined as a relationship between the values. For example, a function f is given as a changes to b such that f of x is equal to y for all x belonging to a, y belonging to b. Types of functions. There are mainly three types of functions: one-one or injective functions, onto or surjective functions, and one-one and onto or bijective functions. Let's discuss these functions in detail. One-one function. A function f in which a changes to b is said to be one-one if each element in a has distinctive image in b. That is, for all x1, x2 belonging to A, such that f of x1 is equal to f of x2, which implies x1 is equal to x2. The one-one functions are also called injective functions. For example, the given function is one-to-one function, as there are distinct images in B for every element in A. Here, the images of P, Q, R, S are 4, 2, 1, 5 respectively. Onto function. A function f in which a changes to b is said to be onto if and only if every element of b is the image of some element of a. All elements of b are used. For example, the given function is onto function as for every element of a, there exists an image in b. Here the images of P, Q, R, S are 4, 2, 2, 5 respectively. The onto functions are also called as surjective functions. One-one and onto function. A function f in which a changes to b is said to be one-one and onto if it is both one-one and onto. The one-one and onto functions together are also called as bijective functions. For example, the given function is a bijective function as it has the characteristics of both injective and surjective functions. Here the images of P, Q, R, S are 4, 2, 1, 5 respectively. Composition of functions. The composition of the functions is defined as applying one function to the results of another function. If a function f in which a changes to b and function h in which b changes to c, then composition of f and h, which is denoted by h o f, is a function from a to c. Finally, we can write h of f of x is equal to h of f of x for all x belonging to a. For example, in the given example, x is fed as an input on which function f acts, and the output of f of x is fed to the input on which the function g acts, which finally gives us g of f of x. Example 2. Show that g o f is not equal to f o g, where f of x is cos x and g of x is 3x square. Solution. We have f of x is cos x and g of x is 3x square. So g o f of x is equal to g o f of x, which is equal to g of cos x equal to 3 cos x whole square equal to 3 cos square x. Similarly, FOG of x is equal to FOG of x is equal to f of 3x square equal to cos 3x square. Note that 3 cos x square is not equal to cos 3x square for x equal to 0. Hence, GOF is not equal to FOG. Invertible function. A function f in which x changes to y is invertible if and only if there exists a function h in which y changes to x such that FOG is equal to Ly and GOF is equal to Lx, where Ix, Iy are identity functions. So h is called inverse of function f and is given by f inverse. For example, here we have the function f of x equal to 2x plus 1 written in a flow diagram. Fed x as input to a multiplying by 2 machine, we get 2x. It is then fed to adding 1 machine which gives 2x plus 1. Consider an inverse function y and it goes the other way as y is fed to a subtract 1 machine which gives y minus 1, which is fed to a divide by 2 machine which gives y minus 1 by 2. So, the inverse of function 2x plus 1 is y minus 1 by 2. Examples. Example 1. Let A be the total number of students, that is 50 of class 10th in a school. Let f colon A changes to n be a function defined by f of x equal to roll number of the student x. Show that f is 1, 1 but not onto function. Solution. Step 1. 2 different students of the class cannot have same roll number. Therefore, f must be 1, 1. Step 2. We can assume without any loss of generality that the roll numbers of the students are from 1 to 50. This implies that 51 in n is not a roll number of any student of the class, so that 51 cannot be an image of any element of x under f. Hence, f is not onto. Example 2. Prove that the function f in which a changes to a, given by f of x equal to 2x, is 1, 1 and onto. Solution. The given function f is 1, 1 as f of x1 equal to f of x2, which implies 2x 1 equal to 2x2 implies x1 equal to x2. Also, given any real number y in R, there exists 2y in R such that f of 2y equal to 2 times 2y equal to 4y. Hence, f is onto function. A binary function. A binary operation star defined on a set B is a function star in which the Cartesian product of B and B gives B. Note, the operator star AB is denoted by A star B. A binary operation star defined on a set B is said to be commutative if and only if A star B is equal to B star A for all AB belonging to B. Example. Show that the operator plus in which Cartesian product of R and R gives R given by AB gives A plus 4B square is a binary operation. Solution. Since the operator plus carries each pair AB to a unique element A plus 4B square in R, consider A equal to 2, B equal to 3. So the pair 2, 3 is equal to 2 plus 4 times 3 square, finally, which gives 38, which is also belonging to R. So the operator plus is a binary operation on R. But let us summarize what we have learnt in this chapter. A relation R in a set B is called empty relation. If no element of B is related to any element of B, that is, R is given as null set, being a subset of Cartesian product of B and B. A relation R in a set B is called universal relation if each element of B is related to every element of B, that is, R is equal to the Cartesian product of B and B. A relation R in a set B is said to be an equivalence relation if R is reflexive, symmetric and transitive. A function is defined as a relationship between the values There are mainly three types of functions: one or injective functions, onto or surjective functions, and one and onto or bijective functions. The composition of the functions is defined as applying one function to the results of another function. A function f in which x changes to y is invertible if and only if there exists a function h in which y changes to x such that f of g is equal to iy and g of f is equal to ix, where ix, iy are identity functions. So h is called inverse of function and is given by f inverse. A binary operation star defined on a set B is a function star in which the Cartesian product of B and B gives B. Let us summarize what we have learnt. The equations which involve variables as well as derivatives of the dependent variable with respect to the independent variable are known as differential equations. Order of a differential equation. It is defined as the order of the highest order derivative of the dependent variable involved in the differential equation. Degree of a differential equation. For a differential equation, its degree implies the highest power of the highest order derivative involved in that particular differential equation. The function which contains arbitrary constants is known as the general solution of the differential equation. The solution obtained from the general solution after providing the values of the arbitrary constants is known as particular solution. The methods of solving differential